A single modern medical scan generates an enormous volume of high-resolution, multidimensional data. Extracting value from these scans requires advanced techniques like automated tumor segmentation and predictive radiomics, which force algorithms to process billions of variables simultaneously to identify subtle tissue anomalies. For decades, classical hardware kept pace, but as the physical limits of Moore's law plateau, the escalating computational demands of iterative image reconstruction are outgrowing conventional silicon. Training sophisticated predictive models and analyzing raw, multidimensional case-based data now routinely requires petaflop-scale computational resources. Simply adding more classical processors creates latency and energy costs that make real-time clinical analysis unviable. Bypassing this bottleneck demands an entirely new computational architecture. Quantum computing offers a theoretical solution. By exploiting superposition and entanglement, a quantum processor can evaluate entire multidimensional data arrays simultaneously. But today's hardware is bound by the constraints of the noisy intermediate-scale quantum, or NISQ era. These devices have limited qubit counts and extremely short decoherence times. Before a quantum machine learning algorithm can even begin its analysis, the classical image data must first be mapped into a quantum state, a process known as quantum image representation. This creates a mathematical paradox. Legacy representation algorithms require a massive amount of logical operations, scaling quadratically with the resolution of the image. Because the resulting circuit depth is massive, the quantum state loses coherence and collapses into noise before the image finishes loading. A new framework called QPIXL addresses this by achieving optimal linear scaling without demanding extra resources. By mathematically bypassing the data loading bottleneck, QPIXL aligns the software requirements of medical imaging with the specific physical constraints of today's processors. To understand the efficiency of QPIXL, we have to look at the baseline standard for encoding, the flexible representation of quantum images, or FRQI. FRQI maps every pixel to a rotation angle on a color qubit. But building this physically requires decomposing massive multi-controlled gates into long strings of basic gates. This cost scales quadratically. As resolution increases, the operation count violently breaches the hardware's maximum coherence time. Previous attempts to flatten this quadratic explosion forced engineers to use extra functional qubits to act as temporary memory, known as ancilla. Any architecture relying on pixel-by-pixel multi-controlled gates is intrinsically incompatible with the stringent constraints of current NISQ hardware. QPIXL succeeds by discarding the concept of pixel-by-pixel multi-controlled gates entirely. It uses a uniformly controlled rotation, expressed as a large block matrix with distinct rotation blocks down its central diagonal. This physically translates into an efficient quantum circuit topology, a repeating, alternating sequence of one rotation gate followed by one CNOT gate. The absolute cost of this new circuit is fixed at exactly 2 gate operations per pixel. This achieves O of n linear complexity. It hits the theoretical mathematical limit for efficiency without utilizing a single ancilla qubit. Flattening the architecture from a tangled hierarchy of controls into a simple alternating sequence physically solves the depth problem holding back near-term quantum processors. But how do we calculate the exact rotation angles for this alternating sequence so it accurately reconstructs the complex details of a medical scan? Through classical pre-processing, raw pixel intensities are mathematically transformed into target angles before touching quantum hardware. First, a scaled Walsh-Hadamard transform exposes non-local spatial correlations across the image. Then, a gray code permutation reorganizes the indices to align with the alternating CNOT control structure. This entire linear system is performed matrix-free on standard classical computers in O n log n time. Offloading the heavy algebraic lifting to classical preprocessing is the prerequisite for generating a circuit that respects the coherence limits of a quantum machine. This linear architecture carries a secondary advantage: algorithmic compression executed directly on the physical quantum circuit. Because the classical Walsh-Hadamard transport exposes redundancies in the image, a large number of the newly calculated target angles end up being essentially zero. QPIXL establishes a strict compression rule. If a target angle falls below a specific threshold, the rotation is deleted. This leaves uninterrupted strings of consecutive CNOT gates. Under quantum mechanics, consecutive CNOT gates sharing a control qubit perfectly annihilate each other. Classical Cree processing runs a simple parity check to determine whether an odd or even number of CNOTs remain, dictating if a gate is ultimately placed or ignored. By compressing the mathematics classically, QPIXL triggers a physical collapse of the quantum circuit, saving vast amounts of critical coherence time. We can observe this impact on empirical data using a 256 by 256 micro-CT scan of a ceramic matrix composite. Material scientists and medical professionals rely entirely on the exact structural geometries within these scans, like circular fiber patterns or tissue boundaries, to make critical assessments. Loading this specific image using an uncompressed FRQI framework demands a staggering 65,536 individual gates. This chart compares the computational payload. Applying a 90% algorithmic threshold collapses the circuit down to fewer than 6,000 gates. Even at this extreme 90% reduction, the macroscopic structure and the fine-scale edge details remain mathematically intact and fully analyzable. Algorithmic gate collapse is a highly selective culling that preserves the exact structural fidelity required for medical analysis. These empirical results map directly to the broader medical imaging landscape, encompassing 3D MRI reconstruction and complex PET radiomics. The absolute rule of quantum computing remains. The future of multidimensional data analysis requires loading information faster than the hardware's strict decoherence limit. QPIXL's linear scaling and physical gate annihilation finally align the theoretical ambitions of algorithm designers with the harsh physical realities of NISQ hardware. It enables a precise hybrid workflow. Classical computers easily handle the Walsh-Hadamard preprocessing, allowing quantum processors to dedicate their coherence time entirely to machine learning and feature extraction. And by completely removing the need for ancilla memory qubits, QPIXL frees up the entire quantum processor to handle deeper multimodal data fusion. By solving the foundational data loading bottleneck, QPIXL clears the path for quantum computing to fundamentally transform the speed, scale, and precision of modern medical imaging.